Alright, so the second part of 3.4 notes is just a couple more examples of applications of exponential decay. So again, I'm just going to do a couple of cases. Again, similar to what we did in the earlier notes of 3.3. Alright, so we know a drug. This would be a biology example. So we did chemistry example earlier. This is a biology example. I suppose that we know a drug decays exponentially in the bloodstream, and we know its rate of decay. Alright, its rate of decay is 13.8% per hour. So that's how fast the body metabolizes it, breaks it down. So it satisfies the differential equation. The change in quantity over time is a negative because it's decaying. 0.138, because it'd be right, the percent is a decimal, times how much we have in our bloodstream, right? Q would be the amount of drug in the body after the time in hours. All right, suppose that you have taken 30 milligrams of this particular drug initially, so that's how much you've taken. So that's your Q naught. All right, find the exponential function that gives the amount of drugs left in the bloodstream, T hours. So again, you have to remember that it's the same exponential equation we had before. Right? The only difference is K is negative, so you don't have to know a new equation. It's the same equation. My initial amount was 30 milligrams. My constant was a negative 0.138. And so my equation, right, write it as an equation because that's what they're asking for, is 30e raised to the negative 0.138 times time, and the units are in milligrams. Alright, so now we're going to use it. So there's the equation, so I'm going to write it here so I have it for the next part. 30e to the negative 0.138 times time. Alright, so the first question, when you only have 20% of the drug in your bloodstream, you'll no longer feel the effects of it. So when your body's decayed, so you start with 100%, right? And when your body's decayed it down to 20%, you no longer feel whatever it does. So if it's a pain reliever, right, it stops working, it's no longer effective. Right, we want to know how long that will be. So this would be, again, when you get your ibuprofen or whatever and they say it works for 12 hours, well, this is what they're figuring out, right? What does it need to break down to? And they usually do it based on averages. Alright, so we want to know how long, so we're looking for the time it will take for the quantity to decay down to 20%. Now, there's two ways to do this. Alright, there's the set it up, meaning we want to find the time where we get down to 20% of what I started with, right? So I started with 30, and I need to figure out, well, how much is left when there's only 20% of it. So I take my 30 times my 20%, and so I want to know when I've decayed down to 6 milligrams, right? 6 milligrams is how much you have left in your bloodstream when 30 milligrams have decayed down to 20, right? 6 is 20% of 30. Alright, and then you can use that to solve. Alright, so I'd set 6 equal to my 30e raised to the k times time and solve for time. Alright, so 6 divided by 30. If you take 6 and divide it by 30, it comes out to be 0.2. And that's not a coincidence. I'll talk about it after I finish solving. Alright, so I get, again, 6. If you take 6 divided by 30, it comes out to the decimal 0.2. Take the natural log of both sides. So I get the natural log of 0.2 equals the decay constant, negative 1.38 times time, and then divide by the negative 1.38. And so the time is going to be whatever the natural log of 0.2 divided by k. Alright, which again, if you type that in the calculator, it comes out 11.66 hours. So the drug lasts for about 11.66 hours. Alright, after that point, the body will have decayed it down to 6 milligrams and you'll no longer feel its effects. Alright, just to kind of set this up and explain it, this is, again, how half-lives and things work. Right? I decayed down to 20%. Well, instead of half of what I started with, I decayed down to 20% of what I started with. And so this works for any percentages, right? It's the natural log of the percent decimal that I want left divided by my k. And so it would work the same way if I said, how long does it take to decay down to 10%? All right, well, if it was 10%, it'd be the natural log of 0.1 divided by k, and that would tell you how long it takes to get to 10%. 50% would be my half-life, which is the next one we're going to do. And so that works the same way. What's the half-life of the drug? Well, I want to know how long it's going to take me to get down to half of what I started with. Alright, so the half-life is the natural log of 1/2, 0.5, divided by my k. Or you could solve it this way. It would work out the same way. You'd take 15 instead of 6, right? 15 is half of 30, and solve it this way. But you don't need to, all right? This always works out for these types of problems. Right? And so I'm just going to use this equation because most of the time students will do that, right? Half-life is the natural log of 1/2, because that's the percent I have left, divided by my decay constant. It comes out to 5.02 hours. Alright, so it takes about 5 hours to, so every 5 hours your body breaks it down in half. So if you start off with 100, in 5 hours you'll have 50, and then another 5 hours you'll have 25, and another 5 hours it'll be half of 25, and so on. It'll continue in that regard. Alright, so the last equation is a similar to logistic type, but it's in terms of and for some reason when I must have put it in this file that was an equal sign, so I'm going to rewrite my equation over here. A decay, so there's not a division, so it's negative 20, again this should be on your set of notes, t plus 20 times e to that negative 0.05 times time plus 400. Alright, we're going to solve this one graphically, and it's going to look like a logistics curve, alright? It's going to look similar to, it's actually not a logistics curve, but it's going to look very similar. Do change your window. This means those would be my minimums, that would be it. So this would be my x min, that would be my x max. Alright, so for both of them, this would be my y min would be 0, my y max would be 500. So when you plug it into the calculator, change your window to 0 to 500 in both the x and the y direction, so it'll be a square window. Alright, so this function represents the total number of new iPhones sold t months after its release, is given by this equation h of t. Alright, so this is the equation that I'm going to graph using my window, and so this would be months, right, because time is in months, and this would be number of iPhones sold. Alright, so when we plug in 0, we would actually start fairly low. Again, I'm just going to mark off where my 0 is. It starts very low, so almost would be close to that axis there, and then it kind of comes up and then levels off. So again, your calculator should look like it's actually a little steeper than what I've drawn in. Alright, and so there's the h of t, which, like I said, it looks very similar to the logistics curve. It's not, because it's totally concave down everywhere. Alright, there's not an inflection point here. Alright, and so we've graphed the function, what's happening in the long run. So in the long run, just in words, after many months, right, that's in the long run, as my months go to infinity, alright, the sales reach a maximum, alright, it tapers off, meaning the rate of sale approaches 0. That's what's happening up here. It flattens out, alright? This would be whatever, again, it's approaching some limiting value, whatever that limiting value would be the maximum amount of iPhones they would expect to sell. So there's going to be a maximum. Alright, when it reaches the maximum, the rate at which they're selling the iPhones will stop, right? Because everybody who has one has already bought it, and so no new people at this end will buy it, right? Because everybody who wanted one has got one already, right? And so that would be, if I'm going off to infinity, my function's approaching whatever that asymptote is. Alright, so the next problem is going to be, well, what is the asymptote? So I'm going to see if I can't figure it out. Alright, so I'm going to find, and I'm just going to use my calculator to do this. So I'm going to use the value key on my calculator. How many iPhones we expect at 1 month, 50 months, 100 months. Alright, so again, you could just, oops, too far. You could plug it in this equation, or since we have the graph, remember you can use the value key on your calculator. I'd probably just use the value key. Alright, so when we plug 1 in, and I'm going to round a few decimal places, remember it's in millions of iPhones. Alright, so it comes out to 0.484 million iPhones sold. Alright, so a little less than 500,000 iPhones after the first month. 50 months, much more, right? Exponential growth, right? 285.08 million iPhones sold. And then 100 months. All right, 3.83.63. All right, which didn't quite give me what I wanted, so I'm actually going to plug in another value. Remember, the edge of my picture goes to 500, so I'm going to plug 400 in. I'm going to add to this. I'm going to plug in 400. All right, so I'm going to find how many were sold after 400 months. And so if we plug that in, it rounds to 400. And again, 400, which is what I picked. If I plug in 450, all right, it also is going to come out 400 million. And so that's what it's approaching. All right, the line that it's approaching up here, this asymptote, is this 400 value. What's happening is, remember, these fractions are going to 0. These fractions are getting really small, right? These are fractions because it's e raised to a negative. Every time I plug a value in, I'm really dividing by that, and I'm dividing by that number exponentially. And so this expression basically gets so small it doesn't matter, this part here. It goes to 0 because I'm dividing by bigger and bigger numbers. And so what I'm left with is that plus 400 at the end. And so that's what this asymptote is. All right, my h of t is approaching 400 million. That would be their expectation. They're expecting, that would be the maximum. They would expect to sell 400 iPhones. That's their expectation. All right, that would be what they would expect. That would be their limiting value. Their expectation is that's the total. After they sell 400, everybody who wanted to buy one has bought one. No more new iPhone people. All right, everybody else has a different type of phone. All right, well, let's see if that still plays with the rate of change. And so what the rate of change is it should be going towards 0, right, as we go out here to the 400 months. All right, so what's happening? It shouldn't be approaching 0, but we're going to plug it in and see. And again, I'm just going to use my calculator. Remember, there's the dy dx key on the calculator. And I can find my derivative. Remember, it's under second trace, the sixth one down, dy dx, and then you plug in your x value. So you select the second trace, the sixth one down, dy dx, and then once you select that, input where we want to find our derivative. All right, so at 50, so input 50. All right, when you plug 50 in, it comes out the derivative 0.724, and remember, it's millions of iPhones, so it's a rate of change, right, derivative, per month, right? That's how fast it's selling after 50 months. So it's selling faster than actually how many we sold, right? We have that many sold, about 500,000. The rate is faster than that, so we're selling more than 500,000 per month. Oh, I'm looking at the wrong one. So we're not. We're here. All right, so we're rate is still over 500,000 iPhones per month. So again, that's the rate. That's not how many we sold. We're selling this amount. And so that would be the rate at which they're selling. That's how fast, right? It's speed at the 5th month. All right, well, plug 100 in and see what its speed is in 100 months. So again, I'm going to use my derivative. All right, when I plug in 100.674 million iPhones per month. All right, so still increasing, but smaller, right? It's about 100,000 less, right? The speed is 100,000 less than at 50. All right, so it's still increasing, but increasing at a slower rate. All right, then we'll plug in our 400. All right, comes out to the scientific notation, right? It's got that 8.2 e to the negative 7. And so what that means is move the decimal place over 7. So that'd be 6 zeros, 8, 2. Well, that's a really small number. We would, again, be perfectly legit to round that to 0. And so after 400 months, iPhones basically aren't selling, right? The rate's so small, it's near 0. So the rate has slowed down. and approaches 0. All right, that's what's happened. The rate's getting smaller. All right, after each month passes, my rate of change is decreasing until I eventually decrease and it slows down and really gets to 0. No new people are buying the iPhone. Again, similar to the logistics curve, right? It has a leveling off. Everybody who's bought one has bought one, and no new people are buying them. All right, so my rate of change is decreasing. So what's happening is the rate of sales decrease over time until it's eventually 0. All right, no new phones are being sold. The rate of change is 0. Everyone who's purchased one has already done so. So no new people are going to buy it. And then that's when they'd introduce a new phone, right? They come into the new phone. All right, we'll stop there. So that finishes it, the set of notes. All right, so we're done. That's the information you'll need to know for the next exam. Make sure you're doing the practice problems and the homeworks, and get ready for the test. All right, and look at Blackboard for updates and announcements. All right, so we will stop that set of notes there.